Light allows us to see objects, communicates information, and records data. A focused beam of light can be used to process materials with high precision, trap microparticles in fluid, or many other tasks. Now, what do you imagine this beam of light to be like? Is it a powerful red beam that extends into space in a straight line? Or a green beam spreading as it travels? Well, you're not wrong. Some beams of light do fit those descriptions. What about a beam that travels in a wavy path like a snake? Do you think it is possible? The answer is yes. It is possible to design the beam of light so that it takes a different transverse profile at designed point along its propagation. In this video, the properties of light that can be engineered will be introduced, and some experimental demonstrations of such properties will be displayed. The light can be designed to take an arbitrary value of degrees of freedom such as the intensity, state of polarization, wavelength, and orbital angular momentum by superposing Bessel beams with different transverse and longitudinal wave numbers and the complex pattern coefficient A that assigns contribution weight to each of the beams in the superposition. By superposing Bessel beams whose amplitudes we can design, the path of the light can be engineered. For example, by superpositioning Bessel beams with different topological charge L, we can have the different central spots of the beam appear or disappear over a certain propagation duration. Another example is engineering the wavelength of the light. By employing Bessel beams with different wavelengths in this proposition, the wavelength of the beam can be changed along its propagation. This equation shows a summation of wave solutions over both wavelength lambda and topological charge L. Now, let's look at some experimental demonstrations of these possibilities. This image shows a longitudinal profile of the structured light with a non-periodic snake-like trajectory. By superpositioning Bessel beams, including the first-order beams with the L value of -1 and 1 within the same space interval, we designed the central spot that propagates off the axis, repeating to travel above and below the axis. Such off-axis propagation of the beam resembles a snake, hence snake-like beam. This video shows the transverse profile of the same beam. From 5 to 25 cm, there is only 0th order Bessel beam contributing to the central spot. Over this propagation range, the central spot maintains a straight course along the propagation axis. From 25 to 65 cm, the beam has non-zero pattern coefficients assigned to first order Bessel beams of L value either -1 or 1. As a result, the central spot travels off-axis trajectory during the propagation. From 65 to 85 cm, the contributions of the first order Bessel beams are turned off again, and the beam travels in the straight path. The second demonstration shows a beam with different wavelengths at different points along the propagation. Using the Bessel beams with wavelengths of 532 and 635 nanometers, this continuous longitudinal profile of multichromatic beam with two alternating colors is made possible. From the propagation distance of 10 to 28 and 32 to 50 cm, the 0th order Bessel beam with wavelength 635 nanometer is assigned non-zero weighting and is assigned zero weighting for the rest of the propagation. This is why the beam appears red in these regions. From 22 to 40 and 44 to 60 cm, the beam with wavelength 532 nanometer has non-zero coefficient, making the resulting beam appear green over these propagation distances. There are some transitional regions too, such as 24 to 47 cm, where both beams with two different wavelengths contribute to the transverse profile. This means the red and green central spots overlap. Looking closely, you can observe the central spot over this range appears in yellow color. Besides the light intensity and wavelength, orbital angular momentum can also be engineered. In the previous video, multiple experimental demonstrations of this concept were shown. Here, this video clip is for a case where both wavelength and orbital angular momentum are controlled. Not only that this beam is multichromatic, changing the colors from red to green in propagation, but the number of petals in the central spot also change. This is possible because from 0 to 18 cm, bezel beams with wavelength 635 nanometer and topological charges ±1 are switched on, showing 2 red petals. And from 12 to 30 cm, beams with wavelength 532 nanometers and topological charges ±1 are used, showing 2 green petals. Similarly, from 22 to 40 cm, 635 nanometer beams with ±2 charges allow the 4 red petals. And lastly, from 34 to 50 cm, 532 nanometer beams with ±2 charges show the 4 green petals. The control over the beam properties allow many engineering applications, including optical imaging, communications, and materials processing. By being able to design the beam path, nano and microparticles may be manipulated with higher accuracy and convenience. By being able to design a multichromatic beam, we can take advantage of a wavelength-specific optical media. These relevant papers are shown for reference or your interest. Thank you for your attention.